Hello and welcome to ENGEN101 21P Workshop 10. And what we're going to be talking about today are vectors. And vectors are an incredibly important part of engineering. So let's start at the beginning. Okay, once upon a time, let's set a problem. So say you have somebody like me racing. And let's say I could run 274 meters in 7 minutes and 55 seconds. 274 meters, and would you be impressed? Well, let's take into account that the record for running 400 meters at the Olympics is 43 seconds. Would you be impressed if I could do 274 meters in 7:55? Most people go, no. But what happens if I point out that 7 minutes 55 seconds is actually the world record for running 274 meters? Why would that be? The answer is, in France, there is a tower called the Tower Eiffel, and from the basement to the top is 274 meters. That's to the top deck. And that is the world record time for somebody to run up that staircase, 1,664 steps in 7 minutes 55 seconds. So does that make a difference? And the answer is yes. I mean, if I'm running it flat, the world record's 43 seconds. If you're going up, it's 7 minutes 55. So what's the difference in this case? And the answer is the direction. So when we're talking a race, for example, the direction becomes really, really important. So not only now do we have a distance, 74, but we also have a direction. And that is a vector. And vectors change the way we have to do mathematics, and quite dramatically so. So in the old days, I mean, vectors used to be used in navigation. So say you're on a sailing ship, well, put a mast up. You might be doing, I don't know, 5 knots that way. There might be a 2-knot current that way. So your actual speed would be that. And if you fail to take into account this 2-knot speed, then you might crash into something. In fact, there's a famous case of the Honda Point disaster in America, where there was an earthquake in Japan, and it changed that current speed. Nobody knew about it, and 6 destroyers went into the rocks because nobody knew of the earthquake. So this is actually quite traditional, adding vectors together. Adding vectors could be in opposite directions. And let's show you how important this is. If I'm going 2 meters per second this way, and there's 2 meters per second current that way, my total speed is 0 meters per second. If I'm going 2 meters that way, and there's a 2 meter current, my total speed could be 4 meters per second. That is a huge variation. So we must have mathematics to take that into account. And that is called vector mathematics. So there's a couple of ways that there's multiple ways that we can represent a vector. The traditional way is the size, 4 meters, and an angle, 60 degrees. And we write that 4 meters, angle 60 degrees. That's a polar coordinate system. That's how people used to do it for a long time. We can also break this up into components. Say we got a triangle like that. I can't remember the angle here. But if we break this up, I'm breaking this up into 3, 4, 5 triangle, that component there, not only can be represented this way, but it can also be represented as an x bit, x equals 4, and a y bit, x equals 3, sorry. And there's a couple of ways of representing that. We can write 4i plus 3j. That's one way of representing it. I is just, I is just the mathematician's way of saying the X amount. J is the mathematician's way of saying the Y amount. And Z is the mathematician's way of, K is the mathematician's way of saying the Z amount. Or I can write it as an ordered pair. So I can write the X bit, then the Y bit, or I can write the X bit, the Y bit, the Z bit. If you're doing relativity, the T bit, that could be an ordered triplet. So that'll be the X bit, the Y bit, the Z bit. That's another way of writing it. This way is a lot easier when you're doing math. If you break it up like this, it's a lot easier to do the math. And you can also do the math in Excel really easy. So you can actually literally just stick it into a spreadsheet. So now that we've got a way of representing vectors, this isn't the only way, but this is the easiest way. We have several mathematical functions that we can do with vectors. If I have a vector, I can add vectors. So A plus B. To show it's a vector, there's several ways of showing it's a vector. We can print it in bold. That's one way of showing it's a vector. We can put a unit vector next to it. Unit vector, sorry, AI. Or we can put something under it. In the trade, this has got a very technical name. It's called a twiddle. So that's the third way of doing it. So I tend to use the twiddle method a lot. But the way that we join vectors A and B together is we join them together like dogs greeting. So A meets B. And it's like dogs meeting, goes nose to tail, nose to tail, nose to tail. We call it the dog method of adding vectors. And I mean, a lot of things, like if we were to take a journey from Hamilton to Auckland, which may be difficult due to COVID, I can break this up into several bits. I can break this up in my journey from here to Taupiri, where there's a service station and a Taco Bell. Then I go up to Pocono, stop there for an ice cream. And then from Pocono, then I go up to Auckland. And you notice I can break my journey up into smaller components, which I can then add together. Dun, 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 dun. But there's other forms of stuff that we can do as well. We can also we can subtract vectors, A minus B. So, I mean, the classic one is if you're talking, say, change in velocity. Now, velocity is a vector because it makes a big difference if I'm doing 10 meters per second that way or if I'm doing 10 meters per second that way. Speed, not so important, but velocity, for example, I have a velocity, I'm going so fast in such and such a direction, usually towards my goal. But say I'm in a racing yacht or something, and I'm going 10 meters per second that way, and there's a headwind that way, or I slow down, and now I'm doing 5 meters per second. Let's say I change direction, I end up going 5 meters per second that way. So A is 10 meters per second to the right, B is 5 meters per second down. So the change in velocity, in this case, is going to equal B minus A. How do I do that? There's a couple of ways. The easiest way is to go B plus negative A. So if A is 10 meters per second that way, negative A is going to be 10 meters per second the other way. So what I do here is I add these together. The change in velocity is going to be that, B plus So nose to tail, like two dogs meeting, minus A, 5, 10, twiddle, twiddle. And that will actually give me my change in velocity. And then I can, in this case, because I've set this up as right angles, I can just use Pythagoras to find out how big that is. Okay, but let's get on to the trickier one. What happens if you want to multiply vectors? I mean, the trouble is that there's 3 different ways of multiplying vectors. But let's take an example. So let's take work. Work is equal to force times distance. We all got taught that at high school, hopefully. Work is equal to force times distance. It's equal to change in energy. But force is a vector. Force must have a direction. Because if I apply a force that way, it's different than if I apply a force that way. And displacement also has a direction. But, so if I've got a box and I'm pushing it, it travels distance x. Cool. But you also get torque, which is also force times distance or displacement. These are not the same thing. These are very different things. Work is not automatically equal to torque. I mean, in this case, with an arm, you have a fulcrum, you have a distance, you have a force. So the big question here, these are not the same thing. How do we tell these apart? Why are these different? And the answer is very simple. This is a dot product. This is a cross product. And I know this because in this case, the force and the displacement are in the same direction. Work the same. With torque, the force is going downwards, the displacement's that way. They're at right angles. And that's a cross product. So we have dot products, cross products. A couple of things to remember. The product, dot product, gives you a scalar. So that's going to be a scalar. Dot product give a scalar result, which means it has size but no direction. Cross products give a vector result. This is also really important to remember as engineers. So that torque itself is also a vector. So yeah, unfortunately, vectors are something as engineers you're going to see pretty much every single day, because especially mechanicals, electricals, mechatronics, but also civils, environmental, even environmentals will see vectors pretty much every single day. And vectors turn up in surprising places. I mean, so anyway, I'm not going to get too much more into this. So the big thing we have to remember, we have 2 types of multiplication here. We can add vectors, we can subtract vectors, we can multiply vectors. Dividing, you'll have to talk. These are for when you're multiplying a vector by vector, vector by vector. We also have scalar vector multiplication. So I'm trying to think of a good example. But if you just got a vector V and you multiply it by A, that's what we call a scalar multiplication. So if we have a vector like this, we multiply it by 2, now it becomes twice the line. Anyway, vectors are going to be a standard working tool for you, because when you're building stuff, direction is very important. When they ask you to design and build a bridge, they want a bridge that goes across a river, not a tower. Okay, so good luck on that. I've given you some vector problems to have a crack at and quiz 10 and the quiz, and yeah, hopefully I'll do one more workshop next week on imaginary numbers, and after that I'll mention 201.